Steinhauer here. Welcome back. Continuing our discussion of the sun. Here we have an image, still image of the solar chromosphere seen at the edge of the sun, at least here. And this would be a video. I'm doing this with a PDF, so I can't really play these videos or these animations, which is sad here. I'll post all of these in the supplemental video section below, so you can take a look at these. This would be a nice image of a solar eruption on the surface of the sun. And so we want to talk about sunspots. We talk about other features of the sun's surface that are certainly caused by activity on the surface of the sun. The surface of the sun is not a calm, gentle place. There's lots of stuff going on the surface of the sun. So let's talk a little bit about some of these things. Here we have some examples. And this solar activity is kind of like weather in that things come and go, and there are storms, and there are energetic activities happening on the surface of the sun. And all of these are kind of related, but not phenomenon in terms of what causes them. So, but very different in terms of how they appear, right? Sunspots, we've talked about before. There's very dark spots on the surface of the sun, right? What are these things? And you can see different features of them. They have an umbra, which is the very darkest region. It takes its terminology from shadows. The umbra of the shadow is the darkest part of the shadow, and the penumbra surrounding it is not quite as dark, but still darker than the usual surface. You can see out here the usual granule patterns of the upper regions of convection zones. And those regions don't exist in these sunspot groups. Is this a hole in the surface of the sun? Is it, Galileo thought these might be clouds passing by. He was one of the first to observe these sunspots with telescopes, using the projected image of the sun, of course, not looking right at the sun with the telescope. Lots of you can see even here on the side of the sun, some regions where hot plasma from the surface of the sun has been lifted physically off of the surface of the sun and is being violently drawn out into space. This is one of the most dramatic features. Anytime you have a looping feature like this, where it connects on two ends, and you've got a huge loop of gas and plasma that's been lifted off the surface of the sun, we call that a prominence. And usually these are seen on the edge of the sun in profile. And this is one of the biggest prominences you'll see. This is gigantic. Again, we did this, the Earth to scale is maybe the size of this laser pointer or so. This is just a tremendously large feature and region of space. Solar flares are similar to prominences, except they happen much faster and are typically much more energetic. You have huge amounts of energy pouring out of the sun in copious amounts. And shining quite brightly for short periods of time. And all three of these things are solar activity, and all three of them share a common underlying cause. And let's think about and talk about what that underlying cause is. Here's a sunspot, right? Again, why do they look dark? It is not because they're a hole in the surface of the sun or because there's some cloud covering it up. It is simply because they are cooler than the regions surrounding them in the on the solar surface, right? Remember, the hotter an object gets, or the hotter a gas gets, the more brightly it will glow. It's not like it's cold in the center of the sunspot. It's still 4,000 Kelvin, but it's way cooler than the regions in the penumbra, which is itself cooler than the regions in the normal surface of the sun, which is almost 6,000 Kelvin, right? So this looks dark because we're taking a picture and an image of this where we have this region of the sun that is well sampled. If we took a longer exposure, we would be able to see some things here. It would still be glowing. It just isn't glowing nearly as brightly as the regions around it. So it looks darker. So it looks like a spot on the surface of the sun. So it looks like a sunspot. And we know that these are regions where the sun has very strong magnetic fields poking out through them. You may be familiar with magnetic fields. Any bar magnet that you have will emit magnetic field lines from a north pole and those field lines will stretch through empty space, and they'll come back and can reconnect at the south end of that magnet. And these field lines carry force, carry energy, and they can exert forces on other things. You know this if you try to put two magnets the wrong end together, you have a hard time pushing them together. There's a force. Those magnetic field lines coming out of the north and south end of that magnet prevent them from coming together. And conversely, if you turn it around and put them north to south, that's an attractive force, and those two ends of the magnet will feel attracted to each other and snap together if you get them close enough. So magnetic fields are a real thing. You can experience them in your everyday life, and in the centers of sunspots, they happen to be extraordinarily strong. Now, you might be asking, how do we know that? How do we know that there are strong sun magnetic fields in the centers of these spots? Well, it turns out that there's a process called the Zeeman effect. It doesn't really matter what the Zeeman effect is, but if you look at an absorption line over a sunspot, and this is exactly what we've got here. We've taken a slit spectrograph, and we have put that slit directly over a sunspot. And you can see the regions that are dark here and not green and not bright green are regions where the sunspot is. And the Zeeman effect affects certain lines. So the stronger a magnetic field is, it will take a line that is usually a single line and split it into other lines. Basically, you've got an energy state. Remember how absorption lines are formed. You've got energy states in these atoms where these electrons are. The energy of that atom changes in the presence of a strong magnetic field. And it actually splits it from one energy state into several energy states. And so you can get electrons being absorbed at each of those different energies, and that creates a triple line instead of a single line. And the stronger that magnetic field is, the more it separates them. And so not only can you tell that, yes, the magnetic field is strong, in the sunspots themselves, we can measure how strong it is. And this is one of the major tools we have to figure out how and why these things work. So we know that magnetic fields play a huge role in sunspots. How does this work? Well, as I was mentioning before with bar magnets, here's an example of a bar magnet. You've got a north end and a south end, and you can see here drawn in the magnetic field lines. They exit the north pole, they make this dipole loop and come back in the south pole. And they all are looped like this. They always connect. In fact, it's very difficult to get magnetic field lines that don't connect with anything. This is a bar magnet. It turns out the sun is kind of like a giant bar magnet. Let me draw this in here. The sun basically is a giant bar magnet. I didn't draw that circle very well, but you get the idea. The sun has just like the Earth is a giant bar magnet. The Earth has a north magnetic pole and a south magnetic pole, and this is why your compass works, right? The compass is designed in such a way that it feels a force from those magnetic field lines that points the needle towards the magnetic north of the Earth. And that's how compasses, you can find your way in the woods. Now, from the surface of the sun, this is important because it is true that these field lines can exert forces on objects. And one of the objects that they exert forces on is charged particles. And in particular, if you've got a charged particle here, let's say, I don't know, a proton or something, it can travel freely up and down the field lines, but it doesn't like to cross field lines. It can travel in this direction fine. It feels a force resisting itself from crossing these field lines. And that's going to become important to understanding how and why these sunspots work. So here's basically the idea. The sunspots are regions we know where there is very strong magnetic fields. Strong magnetic fields, by the way, means that the field lines are very close together. When you have a strong magnetic field, it means those field lines get bunched up and crunched up very close together. So how does this, so here's an example of a sunspot and a prominence. You can kind of see the magnetic field lines in this image extending from one sunspot group to another sunspot group. There's almost certainly a sunspot group here, and there's almost certainly another sunspot group here. They almost always come in pairs. And here you can see, almost even follow the field lines as these charged particles are traveling, again, confined to travel along the field lines and can't really travel against the field lines. So why does this work though? How does this magnetic field work, and why does it make the region on the sun cooler at the top where those field lines happen to be strong? Well, let's draw a picture. Here is the surface of the sun. Now we know normally, here is the surface of the sun. Now we know normally that how does the surface of the sun get heated? Well, we know that there's hot gas rising from below. We know that gas reaches the surface, it radiates away its energy, it cools off, and then it comes over here and it cycles back down. Basically, the surface of the sun is constantly looping gas, hot gas rising up, radiating away energy, and sinking back down again. So what happens when we get a bunch of field lines? So let me draw some strong magnetic field lines over here poking out through the surface of the sun. What happens? Well, we know that charged particles, and there's lots of charged particles on the surface of the sun, most of them are ionized, meaning there's so much energy that the electron's been lost. So most of the hydrogen atoms anyway on the surface of the sun are charged particles, have some electric charge. We know they can travel fine along these field lines, right? But they can't travel across the field lines. And that actually is very efficient at stopping this convective process, because this particle of gas at the top is trapped there. It can't move left or right. It can't get out of the way of the regions below so that more hot gas can come up from below. Without this being able to move to the side, convection basically stops. You have disabled the convection in that particular region. And so what happens? Well, this region of the sun is radiating away its energy, and there's no hot gas coming up from below to replace it because it can't reach that surface. And so what happens? The region where these magnetic fields are very strong cools off. So you might get a whole region here where the surface of the sun gets cool, much cooler than it is in the regions around it, where this convection cycle can continue to take place. So that's why magnetic field, why sunspots are cool. These magnetic fields inhibit convection, which makes the surface of the sun cool off. Okay, I've got a couple of cool videos of solar prominences going off, and you can just see and hear the rain. It's not rain. So the magnetic fields burst through the surface of the sun. They drag a bunch of this hot plasma with it, and then that plasma, and this is a prominence, and then that plasma drains back down. I'll post the video. You can take a look at it. It's pretty cool. Here's another one with a coronal mass ejection, a very high energy. This is a case where the magnetic field lines actually get twisted so much that they break apart. And when they break apart, it releases usually a huge amount of energy, and all kinds of stuff comes streaming out of the sun when these things happen. Coronal mass ejection, literally what it means. In the corona of the sun, well outside the usual chromosphere, you've got a region where you're just emitting huge amounts of energy, matter even, being relayed into space at high speeds. Okay, now all of this matter, all these charged particles that are getting flung into the interstellar space can be a problem for Earth, right? This is sometimes known as a solar wind, because there are typically at all times there's a stream of charged particles coming out of the surface of the sun, and these charged particles can reach Earth. They do reach Earth, in fact. The Earth has its own magnetic field, and its own magnetic field actually is good because it protects us from these charged particles. Again, when the charged particles reach Earth, they don't like to cross these field lines, right? This is shielding us from the majority of these high energy particles that are trailing in. What can happen though, is sometimes they get caught along these field lines, and instead of getting buffeted one way or the other, they actually get caught up in them. and can spiral in and can intersect with the Earth's atmosphere, usually at high latitudes, either near the North Pole or the South Pole. And when these charged particles do interact with the atmosphere, it can glow. And depending on what it hits in the atmosphere, it can glow in different colors. And this is what's known as the Northern Lights, or the Aurora Borealis, or the Southern Lights if you're in the Southern Hemisphere, the Aurora Australis. At certain times of the magnetic cycle, these charged particles are coming in quite frequently, and you'll get whole light shows. I've never seen one of these Northern Light shows, but they are spectacular. I will post another video down in the supplemental materials that shows a time-lapse video of a particularly intense and powerful Northern Lights show. It is spectacular. It's on my bucket list to get to a far northern site when these lights are happening to see this. Hopefully someday I will. Hopefully someday you will too. Put it on your bucket list too. It's worthwhile. Okay. When particularly violent coronal mass ejections happen, and they happen to be pointed at Earth, though sometimes even our magnetic fields aren't enough, and these guys can be pushed, and they can impact things like low Earth satellites, where communications satellites can be disrupted. Even if they're powerful enough, it has been recorded that at certain times it has interrupted the energy supply on Earth. It has interrupted the power grid. These events and storms can be so strong. So our magnetic field does a good job of protecting us, but in a particularly violent event, that doesn't even really help, and bad stuff can happen on the Earth. So it's useful to know about how the processes work, and it can actually have a direct impact on Earth for these various reasons. Okay, now I mentioned the solar cycle before. It turns out that the number of sunspots that you see on the sun and the amount of solar activity in general doesn't stay constant. In fact, it varies dramatically from one year to the next to the next. Here is an example of one way to measure the amount of activity on the surface of the sun. This is the percentage of the sun's surface that's covered by sunspots. Kind of like how many sunspots there are, except measuring it a slightly different way. And you can see a very regular pattern. Look at this. From 1900 to, this is 100 years worth of data, a very regular pattern of high activity and low activity, and high activity and low activity. And this is called the solar cycle. And very regular, like clockwork, every 11 years, the sun goes through this pattern of high sunspot activity and low sunspot, high sunspot, low spot, high sunspot, low spot. And this goes for all of the magnetic activity on the surface of the sun. The prominences and the solar coronal mass ejections and the solar flares and all these things are at a maximum at one point, and then 5.5 years later they're at a minimum, and then 5.5 years later they're at a maximum. The whole cycle lasting from peak to peak or minimum to minimum about 11 years. It's not all that happens. Early in the cycle, it seems that sunspots, this is now latitude and where sunspots are occurring on the surface of the sun in its own latitude, right? So this is the equator of the sun. The sun is rotating just like the Earth is. And this is more, as you go north, more northerly latitudes. And as you go south from the equator, more southerly latitudes. And you can see at the beginning of the cycle, let's look at this one that started at about 1912. Most of these sunspots were coming at high latitudes. And as the sunspot cycle progressed and reached a maximum and then petered out again, the latitude gradually shifted from these northern latitudes to near the equator in both directions. They started out at high latitudes in the north and the south, and eventually drift at the end of the cycle to being situated near the equator. This is called the butterfly diagram, because when you put these things together, it kind of looks like a butterfly in the north and the south. But this is another effect of this 11-year cycle, up and down. So what the heck could cause this? Why does the magnetic activity change on the surface of the sun over an 11-year cycle? It has to do with the winding and the twisting of the fields. This is something that doesn't happen on the Earth because the Earth is a stationary and solid object. the entire Earth rotates at exactly the same rate because it's a solid chunk of rock, basically, except for the center where there's some motion going on. But that's another story. The sun is very much not like that, right? It turns out that the equator of the sun rotates faster than the poles. And I'm not just talking about faster because it's further out and it has further to go. The Earth's equator rotates faster too, but I'm talking about it takes less time for the material on the equator of the sun to make one complete revolution around than it does the poles, right? So this is physically rotating at a faster rate than the more northerly latitudes. And this causes the magnetic field, which would be nice and stationary like a bar magnet, to become twisted. Remember that charged particles don't like to cross magnetic field lines, and that's true. When the field lines are really strong, and you're just talking about single particles, they can't really cross those lines. But the other case is true too. Magnetic fields don't like to cross charged particles. And when you're talking about huge bulk motions of lots and lots of charged particles, they can actually drag the field lines with them. And so what happens is, because the sun's equator is spinning at a faster rate, the sun's magnetic field slowly get wound up over time. And this is what happens. This is what causes sunspots. The magnetic fields get wound tighter and tighter and tighter. The closer these magnetic field lines get together, the stronger the magnetic field is. And kind of like taking a rope. If you've ever taken a rope and just twisted it and twisted it and twisted it and twisted it, it gets more and more twisty. What happens to that rope eventually? Eventually, a kink develops in that rope, and it bursts out, and it can burst out through the surface. The same thing happens with magnetic field lines on the sun. As they get twisted more and more and more, they can develop kinks, and those kinks can poke through the surface. And when they poke through the surface, they usually develop in these sunspot pairs, where one of the sides of the kink is a sunspot over here, and the other side of the kink is a sunspot over there. And so this winding and winding of the magnetic fields, making them stronger and stronger, is what causes the sun to go from solar minimum all the way up to solar maximum. Now, you might be asking yourself, what causes it to go back down again? Wouldn't this process keep going and going and going, and the solar cycle and the magnetic activity just get higher and stronger and stronger? The answer is no, because something dramatic happens about halfway through. When it reaches solar maximum, there is so much activity going on the surface of the sun, and it's gotten wound so tightly that the entire magnetic axis of the sun and the polarity flips completely over. And so once the total magnetic activity of the sun flips over again, flips entirely around. So in other words, we go through this cycle, and if we were to go to the next stage, we would have the sun down here, and it would be a bar magnet, except south would be on the top and north would be on the bottom, right? And once that happens, you're sort of like twisted in the wrong direction. And now instead of twisting it up, you're kind of untwisting your magnetic fields, and the whole system kind of resets. And this is why the magnetic activity in the sun goes down, and we reach a solar minimum as the whole thing recalibrates itself and becomes more like the picture that you see on the left. And the whole cycle starts over again with south on the top and north on the bottom, and the whole cycle starts again. The field lines get wound tighter and tighter and tighter, magnetic activity starts, sunspots crop up, and then the whole thing flips again. And then north will be on top and south will be on bottom. So the solar cycle, the sunspots come and go on a cycle of 11 years, but the true solar cycle is 22 years, because that's the time that it takes to go from solar minimum with north on top to again solar minimum with north on top. You have to go through 2 of these cycles to get back to the original place where you started from, which is low activity and north in one particular direction. Now, this is the cartoon version of this. The real version of this is much more complicated than that. Again, this is another video that I'll post down below, but you can see the hairs on the sun and these are measured magnetic fields on the surface of the sun from January 1997. And you can see, I don't know which is which, it doesn't really matter. One of these colors is a North Pole, and one of these colors is a South Pole. And the point of showing this video is to show that it's much more complicated than the cartoon version that I just drew. Yes, we certainly have a North Pole and a South Pole here, but the flip point isn't just a switch turning and flipping from one to the other. The magnetic fields themselves get tangled and twisted and convoluted and chaotic, and it's a very chaotic process to go from north up to north down. And you can see that in the video that I'll post. Okay, so where are we in the solar cycle now? You can see the last several solar cycles here. In fact, we are basically at solar minimum. We're just coming out of solar minimum right now. In 2020, we had, I'm taping this in March of 2021. In 2020, we were basically at solar minimum. And they've just recently, in the past few months, announced that we are entering the actual next solar cycle. And so magnetic activity is starting to ramp up a little bit on the surface of the sun. There was a year or so where there wasn't much going on at all. And now slowly sunspot activity is starting to ramp up as these field lines get twisted and twisted and twisted. These are different models for how people think this next cycle is going to go in terms of the number of sunspots. You can see not all solar cycles are created equal, right? This one from 1975 to 1985 was really strong, one of the strongest of the last century. This one that we're just ending was the weakest of the entire last century. Why this is, we're not really all that sure, but people are guessing, I'm seeing, that this next one will be a little bit stronger than the one that just ended was. Great, that's it.